Good morning, ma'am. My name is M. Varshasri and I'm studying in second BTech first semester at in CSM branch. And today I'm here to give a PowerPoint presentation for the topic minimal spanning trees on the subject discrete mathematics and graph theory. And the subject code is 23MET07. The introduction to the minimal spanning trees. A minimal spanning tree, which is also known as the MST, is a subset of edges from a connected graph that connects all vertices with the minimum possible total edge weight. It is crucial in various applications, including the network design, clustering, and the allocation. Understanding the minimal spanning trees involves the algorithms like Kruskal's and Prim's, which efficiently find the minimum spanning tree in a graph. In the given example graph, the spanning tree cost is total 2 plus 3 plus 1 plus 3 plus 2 plus 1 plus 5, that is total is equals to 13. Whereas in the view of the MSTs, the last picture is the minimal spanning tree. The key concepts of the graph theory. A graph consists of vertices, which is also known as the nodes, connected by the edges, which is also called as the lines, that may have weights representing the costs or the distances. A connected graph allows for a path between the two vertices, which is essential for constructing a minimal spanning tree. The weight of a spanning tree is the sum of the weight of its edges, and the goal is to minimize this weight at an minimal spanning tree. In a given tree, the sum of the weights of its edges and the goal is to just minimize the weight. The properties of the minimal spanning trees. And minimal spanning tree for a graph is not unique. Multiple minimal spanning trees can exist for a single graph if there are equal weight edges. The number of edges in a minimal spanning tree is always equals to the number of vertices minus 1. That is, for the given graph, if the number of edges is to be found out in the minimal spanning tree, then it is always equals to the number of vertices in a tree minus 1. The minimal spanning trees are acyclic, meaning that they contain the no cycles, ensuring that all vertices are connected without the redundancy. The minimal spanning trees. For the given tree, select an edges in a connected and an undirected graph. The undirected graph means there is no direction to move. From a tree that connects all the vertices, which is known as the spanning tree, minimize the total edge weight of the spanning tree. So the red colored highlighted one is the minimum path cost, which can lead to and gives us the minimal spanning tree. The Kruskal's algorithm overview. The Kruskal's algorithm builds an minimal spanning tree by sorting all edges in ascending order of their weights. It adds edges to the minimal spanning tree one by one, ensuring no cycles are formed until all the vertices are connected. This greedy approach is efficient for the spare graphs and is often implemented using a union find data structure. Kruskal's algorithm is one of the important algorithm in the minimal spanning tree. It adds the edges to the minimal spanning tree one by one, where there are no cycles are formed. We have to see that the no cycle is formed among the edges that are connected to each other. Then that particular graph is said to be in the minimal spanning tree, which is formed by using the Kruskal's algorithm. The example of Kruskal's algorithm. Consider a graph with the vertices A, B, C and D, and the edge weights with the examples AB. The edge weight of AB is 1, the edge weight of AC is 3, the edge weight of BC is 2, the edge weight of CD is 4. First of all, sort the edges, that is AB of 1, BC of 2, AC of 3 and CD of 4, and add AB and BC to the minimal spanning tree. Finally, that is what the cost of spanning tree is 11. That means 4 plus 5 plus 2. Finally, add the AC to connect all the vertices, resulting in a minimal spanning tree with a total weight of 6, as there is no loop is formed in the third picture where it starts from the AB, BC and the AC, which is the minimum spanning tree for the given Kruskal's algorithm. The Prim's algorithm overview. Prim's algorithm starts with a single vertex and expands the minimal spanning tree by adding the lowest weight edge from the tree to a new vertex. It continues the process until all the vertices are included in the minimal spanning tree, maintaining the connectivity and minimizing its weight. This method is particularly effective for the dense graphs and can be implemented with the priority queues for the efficiency. In the Prim's algorithm, first a edge or a node can be selected and then the edge is connected to the least way edge cost, that is known as the Prim's algorithm. The example of the Prim's algorithm. Given a graph with the vertices A, B, C and D and the edges AB and edge weight is 2 and the AC which edge weight is 1 and the BD edge weight is 3 and the CD whose edge weight is 4. Starting from the vertex A, the edge weight of AC is added first, followed by the edge weight of AB which is 2 to include the B. Finally, adding the BD, that means the weight edge cost is 3, connects all the vertices, resulting in a minimal spanning tree with a total weight of 6. This scenario is observed in the Prim's algorithm, which is one of the most important algorithm in the minimal spanning trees. The applications of minimal spanning trees. Minimal spanning trees are widely used in a network design, such as the designing efficient communication or the transportation networks. They help in clustering the algorithms by connecting the points in a way that minimizes intra-cluster distances. Additionally, minimal spanning trees play a role in resource optimization, ensuring the minimal cost in connecting the entities. The challenges and the limitations. Finding a minimal spanning tree in a non-connected graph is impossible, as all the vertices must be reachable from one another. The presence of negative weight edges can complicate the process, though minimal spanning tree algorithms can still handle them effectively. Computational complexity can increase for very large graphs, making it efficient algorithms essential for the practical applications. The conclusion and the further reading. The minimal spanning trees are the fundamental in graph theory with significant implications in the real-world applications. For further exploration, studying the advanced algorithms and their complexities can deepen the understanding. Resources like the textbook on graph theory and online courses provide comprehensive insights into the minimal spanning trees and their applications. Thank you for giving me this opportunity to give a PowerPoint presentation on the minimal spanning trees.